Hello there, Algebra students. This is Mr. Kashi speaking. In this video, what I'm going to be doing is I'm going to be going through the lesson on 7.3, which is on the method of elimination using adding and subtracting. There's 4 slides here of different examples of how to use the elimination process using for the systems of linear equations. So just same as we've been doing is we have 2 lines here and we want to find out where they cross. And so when we have solved this, our solution will be a point xy. And for the elimination process, basically what we are doing is we are just adding or subtracting whole equations in order to eliminate a variable. So in a lot of these examples, it's going to be clear on which variable we're going to be eliminating. And some we're going to get into some more in our next section that it's not going to be clear which one's going to be eliminating. So if you take a look at these 2 equations, 3x plus 5y equals 11, 5x minus 5y equals 5, you can tell that these 2 right here, they're opposite. One's a positive 5, one's a negative 5. And what this tells us to do is that we need to add the 2 equations together. Okay, when we add those 2 equations, okay, and we're just going to add it like we used to add 3 4-digit numbers in elementary school. When we add those 2, this 5y plus a negative 5y is going to cancel out. So we have 3x plus 5x first. We have that would be 8x, and then 5y plus a negative 5y. Well, that would technically be a 0y if you want to write it in. And then 11 plus 5, that gives us 16. So because we have a 0y here, that means that we've eliminated our y variable. So we just get 8x equals 16, which is the whole name of the process is elimination. So to finish up, we divide by 8 on both sides, and we get x equals 2. Now, like I stated before, our solution would be an x and a y. So we found our x, but we haven't found our y yet. In this case, we can plug our x equals 2 into either equation. It doesn't matter. I'm going to take that x equals 2. I'm going to plug it right in there for x. And so here we have 3 times 2 plus 5y equals 11. So then we just got to multiply that out. We got 6 plus 5y equals 11. Then I would subtract 6 on both sides. We would get 5y equals 5. Then I divide by 5 on both sides. I get y equals 1. So now, after plugging that in, we were able to find our y value. And then that would bring us to a solution of the ordered pair 2, 1. And just to reiterate, these are 2 lines. They're written in standard form. We found out where they cross. They intersect at the point 2, 1. Go ahead and pause or rewind if you need more time to jot that down, but I am going to move on to our next example here. So this example just writes out exactly what it's saying, and we have to translate it into a mathematical sentence first, and then we need to solve or find out what the numbers that they're talking about. So the first thing is it says 7 times a number minus 4 times another number. So we have to come up with variables there, and we're just going to stick with x and y. So when they say a number, we're going to talk about x. Another number, they talk about y. So 7 times a number minus 4 times another number is 13. Then the next sentence, negative 7 times a number plus 7 times another number is 14. So now we have that. Because these are opposite, then we're going to add these two together. So when we add these these equations together. The x's cancel, so I'm not going to write anything there. But we have a negative 4 plus a negative 4y plus a 7y would give us a positive 3y. And then adding the 13 plus 14, that would give us 27. Don't forget to add these numbers on the right-hand side of the equation. Then we just simply divide by 3 on both sides. We get y equals 9. Once again, now we found one variable. Now we got to plug it in. Now here we found y. So we need to plug 9 in for y. I'm going to do that right there. So we have 7x minus 4 times 9 equals 13. You could have plugged it into for the 7y in the equation below. It doesn't matter. You should be able to get the same answer either way. But here we have 7x minus 36 equals 13. And then we're adding 36 on both sides. Try to get x alone here. We have 7x equals 13 plus 36. That would be 49. And then divide by 7 on both sides. That conveniently gets us a 7. So once again, we can have our solution. Just because we found x second, make sure that we put it first, though, in our ordered pair. It doesn't mean that it goes second in our ordered pair, because we have, remember, x and y. So our x would go first, which is 7, and then 9. This is our full solution, that point in which those two lines cross. So both these examples dealt with adding the two equations. So I wanted to do a couple that deal with subtraction. So here's one. We have 3x plus 6y equals 30, and 5x plus 6y equals 6. And these right here, those are the exact same. So if they're the same, that tells us to subtract. Okay, so we're going to subtract these two whole equations. We have a 3x minus a 5x. That would give us a negative 2x. And then a 6y minus 6y. Those would cancel. So then we get equals 30 minus 6. This would be a 24. And then just have to go one step further. Divide negative 2 on both sides. X equals a negative 12. So we have our x coordinate in this case. Now we can plug this x into, it doesn't matter, either equation. I'm going to go to that top equation up there. So we're going to go 3 times negative 12 plus 6y equals 30. This would be negative 36 plus 6y equals 30. Then I'm adding 36 on both sides. We would get 6y equals 30 plus 36. That would be 66. And we divide 6 on both sides. We get y equals 11. And once again, if you were to plug that into the bottom equation, the 5x plus 6y equals 6, you would still get the same, should still get the same solution, which if we bring these together, it would be negative 12, 11 as a final solution. So we have one more problem left. It is a word problem, but dealing with the same problem. We have Mai and Kara. They build computers from parts and sell them to make profit. May can build a computer in 0.9 hours, and Kara can build one in 1.2 hours. During a typical week, May and Kara can spend a total of 15 hours building computers. Then, one week, May builds twice as many, and the two spend 24 hours on their project. So, how many computers do May and Kara each make during a typical week? So here we have to actually create our system of equations. So we're going to come up with some variables here. So this would be number of May's computers. and K we're going to have equal number of Kara's computers. Okay, so that first week that they talk about, May has 0.9, so we're going to have 0.9 M plus Kara has 1.2. Okay, and then they both together have the 15 hours, so that'd be equal to 15. Then the next one is May builds twice as many computers. So instead of the 0.9, that's going to be 1.8. Twice as many. And then Kara's the same here. But together they had 24 hours. Okay, so now we want to find where these two cross. So because these two are the same, we're going to add. We're going to subtract. My bad. Okay, we're going to subtract. So 0.9 minus 1.8, this would give us a negative 0.9 M. These two would cancel. And then we have 15 minus a 24. That would be a negative 9. So now it looks like doesn't make a whole lot of sense with all these negatives, but if we divide this out, negative 0.9 on both sides, we find out that May is 10 computers. So now that we know May's, we can find out how many Kara has by plugging this in. So I'm going to take this and I'm going to plug this in right there. So we have 0.9 times 10 plus 1.2K equals 15. So this first multiplication, 0.9 times 10, we just move the decimal point over 1. So we get 9 plus 1.2K equals 15. Here we'd subtract 9 on both sides, and we get 1.2K equals 15 minus 9, that would be 6. And we're going to divide by 1.2 on both sides. And K would equal 5. So usually at the end of a word problem, something like that, you want to kind of explain what you found. Okay, I'd say something like May created 10 computers. Kara created 5 computers. Right? And I will be obviously available to answer any questions that you might have in class about these examples.